All right, we can go ahead and get started. Welcome, everyone. Thank you for joining today. We're happy to have you here and appreciate you taking the time to join this talk. Before we begin, let's take a moment to reflect on the land that we are on and its history. We acknowledge that the land that we are meeting on today is the traditional territory of many nations, including the Mississaugas of the Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples, and is now home to many diverse First Nations, Inuit, and Métis peoples. We are most grateful and respectful for the use of this land. It is my pleasure to introduce our speaker for today's session, Professor Nawaf Mohammed. He's an independent researcher, actuarial science and statistic, and assistant professor at University of Central Missouri. Today's talk is going to focus on extremal additivity of value at risk. Thank you for joining today, Professor. We're excited to learn from your work. Please take it away.
Hello, everyone. Can you hear me?
Yeah.
Thank you for having me today, and it is a great pleasure to be here. Let me just introduce myself. My name is Nawaf Mohammed, and I am a York University graduate. I did my PhD from 2018 till 2023 under the supervision of Dr. Furman, so the founder of RISC. So you're in good hands with him. Today's topic is about the theme of risk measures generally, and specifically about the value at risk. If you're familiar with risk measures, then you're probably familiar with the value at risk being the oldest and most prominent one. So let's get started. Shall I share my screen?
Yeah, for sure.
Okay. So the topic will be about extremal additivity properties of the value at risk. And we will define these properties soon. But before we do that, let's take a refresher on risk measures in general. As you all know, probably from your previous studies or your current studies, we usually want to work with risk measures that capture the financial structure or the properties of financial products or financial phenomena. And those properties, they come together to give us the coherent set of risk measures. So we say a risk measure is coherent, and that definition goes back to Artschner et al. From 1999. If it satisfies, if the functional or the function rho, which takes in a loss and spits out a number, that number is the riskiness of that loss. If that rho satisfies those four properties, then we say that this risk measure is coherent. The first property is translation invariance. So translation invariance means that if you take the uncertainty, the loss X, and you add in, let's say, a liability, a constant liability, then your riskiness doesn't really change with respect to X. The only thing that you do is you add A to the already established risk of X. In other words, if you add any deterministic quantity, then that quantity doesn't change the inherent riskiness in a stochastic way. It changes it deterministically by just adding that A to the risk measure itself. The second property is positive homogeneity. Now, if you consider a risk X and a loss X, and you multiply it by a positive constant C, then the risk measure should scale by that same constant C. Of course, C being positive. You can think of X, let's say a loss denoted in Canadian dollars, then you add, or you want the risk to be measured in let's say euros, then you do an exchange rate, right? That C could be like an exchange rate where you just change the denomination essentially. So your risk measure doesn't really, the risk measure itself stays the same. However, you only change the multiplicative C with respect to it. So rho of X multiplies by C. You only change the denomination. The third property, which is monotonicity, that property is defined as considering two losses. If you have one loss that is dominating another loss, so one loss is likely to give you a higher value with a higher probability, then your risk measure rho should reflect that, meaning the riskiness of x1 should be bigger than the riskiness of x2 whenever x1 is dominant. And finally, the fourth property, which is subadditivity. Now, this is the most important property with respect to coherent risk measures and risk measures in general, the subadditivity property. If you consider two risks, x1, x2, and you add them together, the fact of addition means that you consider a portfolio of those risks. Then subadditivity conveys that the riskiness of the portfolio should be lower than the riskiness of those assets or losses separately. So subadditivity embodies the diversification benefit of pooling your risks together. Now, if your risk measure satisfies all of those four, then you call it coherent. There are examples in the literature of coherent risk measures, and the most famous one is the conditional tail expectation. Sometimes it goes by the name of expected shortfall, as you may encountered it. And it's defined to be the average. Generally, it's defined as, so first of all, a conditional tail expectation is coherent. And it's defined to be at a level P. So we fix a level P that is a threshold that the risk measure measures above. It's the average of the VARs or the value at risks above that threshold P. If your random variable or the loss X is continuous, then we can write it compactly as the expected value of X given that X exceeds the value at risk. So this CTE or conditional tail expectation measure is coherent. There are numerous proofs proving its coherence, its translation invariant, positive homogeneous, monotonic, and subadditive. And the nice thing, if you will, about the coherence of CTE is that it is subadditive for all models that we consider. So that means your losses, X1, X2, think of them as joint model. Then the conditional tail expectation is subadditive no matter what the model is. It could be, bivariate, normal. It could be bivariate, let's say multinomial. It could be anything. Multivariate Pareto, all of the models that you can think of, the conditional tail expectation will always be subadditive. Now, in the definition of the conditional tail expectation, we use the value at risk. So what is that component or that quantity? The value at risk, VAR for short, is another risk measure. And it turns out this VAR is not coherent. It is defined to be the infimum of X. This is a mathematical, I know this is a bit mathematical. It's the infimum of X given that the cumulative probability is greater or equal than the threshold P that we fix. In other words, you can think of VAR as being the minimum amount of capital required so that the probability of exceeding that capital is at most 1 minus P. P is that threshold we fix. So for example, if P, let's say 95%, then the VAR is basically that number, that loss, for which the probability that we exceed that loss is at most 5%. Okay. And the value at risk is in itself a risk measure. It has been used quite widely, and it precedes every risk measure there is. As you can see that the CTE, the conditional tail expectation, is just an average of those bars. And the fact that we averaged them out gave us subadditivity and coherence by extension. However, VAR itself is not coherent because there exist models for which subadditivity does not hold. And it turns out that most models will exhibit subadditivity for certain values of P, certain thresholds of that P here, while other P will give us the other inequality, which we call superadditivity. Okay. Yes. So the 1 over 1 minus P is the average, right? So you take the integral from P to 1, and then you divide it by that, the length of the interval itself, which is 1 minus P. That's the intuition behind it. Good question. Okay, so VAR is the component, and then the CTE is just an aggregation, an average of those bars. And the aggregation or the averaging procedure gives us coherence, while VAR in itself is not coherent. Let's take a couple of examples just to show how the value at risk is not coherent, meaning subadditivity is not satisfied. If we consider x1, x2 to be independent, so there is no dependence among the two losses, and both of them are just Bernoulli. So as you all familiar with Bernoulli variables, they take two values, 0 and 1, right? 0 with probability P, and then 1 with probability of failure, or 1 with probability of success and 0 probability of failure, whatever, however you defined it. So let's take the probability of success and failure to be the same, which is 50% in that Bernoulli. And x1, x2, they follow the same Bernoulli. So they're both the same. They both have the same distribution. If we compute the VAR, which is essentially the quantile. Okay, VAR, the value at risk, is the quantile of the random variable. At a level P, for a Bernoulli random variable, it's either 0 or 1, right? As you would expect. So whenever the probability is less or equal than half, then we get 0. If we are above half, then we get 1. That's the individual risks, the x1, x2. And if you sum them up, you either get 0 or 2, right? You get 0 whenever P is less or equal than half, and you get 2 whenever P exceeds half. Now, let's switch to the aggregate risk. In the aggregate risk, which is x1 plus x2, now you're adding two Bernoulli variables. And you know that two Bernoulli variables that have the same success probability gives us a binomial distribution, where the number of Bernoullis will be the number of trials in our binomial distribution. So x1 plus x2 gives us binomial with 2.5. And the VAR of the sum, now we have a binomial. So we will have to work out the inverse of that cumulative distribution function, and you get either 0, 1, or 2. We have 0 whenever P is less or equal than quarter, 1 between 1/4 and 3/4, and then 2 if we are greater than 3/4. Okay, now let's compare this VAR to that VAR. So the VAR of the sum versus the sum of the VARs. Because if we go back to coherent risk measures, we want to compare this, right? The row of x1 plus x2 versus row of x1 plus row of x2. The var of the sum, as you can see here, equals the var, the sum of the vars whenever p is less or equal than 1/4, because both of them are 0. If we take p less or equal than 1/4 or 25%, then the sum is 0, and also var of the sum is 0. So they're equal. Now, if you go from 1/4 to half, so from here to somewhere in the middle here, the var of the sum is 1, while the sum of the vars, it's still 0. So you can see that the var of the sum now exceeds the sum of the vars. Now, when we have p being greater than half and less or equal than 3/4 or 3/4, then var of the sum is still 1. However, the sum of the vars is 2. So now the sum of the vars exceeds the var of the sum. And finally, when we have p greater than 3/4 or 3/4, then both of them will have 2, and that is equality. So you can see that var for this particular model, which is independent Bernoulli's, behaves in a mixed way. So it starts as super additive, the var of the sum exceeding the sum of the vars, and then it switches to subadditivity when p goes above 50%. And this is just an example of the non-coherence of the value at risk. Let's take another one. Probably you're familiar with bivariate normal distributions. If x1, x2 now are bivariate normal, so they're no longer independent, but they have a linear dependence characterized by the correlation rho. I know we used rho here and we used rho here for risk measures, but this rho in here means a risk measure. And that rho here means the correlation, Pearson correlation. Sorry for the confusion. So if our x1, x2 follows a bivariate normal with mean mu1, mu2, and 2 variances, sigma 1 squared, sigma 2 squared, as well as a correlation coefficient, which is rho, then for a standard normal z is a standard normal random variable, you can express the var of each individual xi as mu1 plus sigma 1 times the var of the standard normal. Their sum is simply that mu1 plus mu2 and then var of z multiplied by the sum of the standard deviations. Now the aggregate risk, we get a normal distribution if we add 2 normal random variables, even if they're dependent. The mean of the new normal is mu1 plus mu2, while the variance is sigma 1 squared plus sigma 2 squared plus 2 rho sigma 1 sigma 2. And now we can calculate the var, which is simply mu1 plus mu2 plus the square root, because now we want the sigma of that x1 plus x2. And the sigma of it is just the square root of its variance times the var of the standard normal. Now let's compare these two. We can cancel out the mu1 plus mu2. That goes away. That's just a shift. It doesn't matter. And the comparison comes down to the coefficients of var of z, meaning the sigma 1 plus sigma 2 versus the square root of that quantity there. And as you can see, sigma 1 plus sigma 2 always exceeds the square root quantity, always. You can square both sides, and you get that we have here 2 times sigma 1 sigma 2, while here we have 2 rho sigma 1 sigma 2. But you already know that the correlation coefficient is bounded by 1, so that means sigma 1 plus sigma 2 always exceeds the square root of that. Now, because that's the case, And the sign of the var changes. If we look at the var of z, it starts negative, right? Because think of the standard normal distribution. It's centered around zero, symmetric. And when the probability is below half, then the var of z is negative. So that means the var of the sum exceeds the sum of the vars, because we're comparing now negative values, right? This negative value is bigger than that negative value. This behavior switches when we go beyond one. Sorry, when we go p goes beyond half. Then the var in that case is positive. Var of z is positive, and as we said, sigma 1 plus sigma 2 exceeds or dominates the square root quantity. That means var here is subadditive, while below half it's superadditive. So this is yet another example of the mixed behavior of var. So it starts off superadditive in most cases and then switches to be subadditive. Okay. So with that in mind, we now know that var is not, doesn't follow that coherence nicety. So it's not confined with this strict property. It is both a good thing and a bad thing. Okay. Despite being non-subadditive for all models, var still remains a central value at risk, central measure of risk for practitioners, because it's easy to compute. So they use historical data, they use simulations, Monte Carlo methods. They use, it's well established. So calculating var is super easy for companies, and that's why it still remains relevant. It also, yes, despite being non-subadditive for all models, because we know that subadditivity is regarded as a nice property since it conveys, as we said, diversification. And that's why some practitioners may be reluctant to use var. But on the other hand, on the plus side of var, it can capture superadditivity. So it can capture this opposite phenomenon, that the risk of the sum exceeds the sum of the two risks. Okay, so var is not coherent, but that drawback gives it an advantage, which is that it can capture superadditivity unlike other risk measures. If we go back to the conditional tail expectation, we said it's always subadditive. And superadditivity doesn't get, there is no place for it within the realm of the conditional tail expectation. And in fact, within the realm of all coherent risk measures. Coherent risk measures are restrictive in a sense, because there are some models for which those measures do not give us a meaningful result. So they're infinite. They're divergent. They're not a number. And those models, you can't measure them using a coherent risk measure. While the var, which is just a quantile, can capture those models as well. Even though we paid the price of it being not always subadditive, but we gained a value for it by its ability to capture superadditivity and a wide range of models. Okay. So now the question is, with all of this in mind, across all so we can ask the question now, across all confidence levels P of the var, under which joint models, x1 to xn, so we generalize now, we don't need to be confined to the bivariate case. So under which joint models is var subadditive additive, or super additive. Again, across all confidence levels, all confidence thresholds P being between 0 and 1, which models will give us super additivity for all P, and which models will give us super additivity, sub-additivity, sorry, for all P. And what about additivity also for all P? And this is the central question behind our results here. Because as we said, that VAR has mixed behavior, right? It is sub-additive and super additive for most models. And now we want to know which models will give us that pure extreme behavior, extreme additive behavior of VAR, whether it's super additive, sub-additive, or additive. We will be dealing with random vectors. Those are just the collection of the losses, x1 up to xn. And we will denote the aggregate risk S. And we will focus mainly on one-sided risks. So each x is supported either from, let's say, 0 infinity or from negative infinity to 0. So one-sided risk can either be right-sided or left-sided. Okay, so we'll focus on one-sided risks. And the first thing, or the setting we will be working with is right-sided risks, because those are the most relevant to us, since we're considering losses, right? And the risks we're talking about, their lower endpoint is 0, because this is natural for us. So why did we consider risks? Because they model low losses, insurance losses, insurance claims, operational risk, where we only want the loss part of our uncertainty. And it is a natural domain, between the natural domain being from 0 to infinity. And the most important thing is that confining ourselves to right-sided risks, and then later on we will deal with left-sided risks, lead to really, really good results. And after that, once we study this in detail, so we study risks that are supported from 0 to infinity, then we can generalize for any risks that start from their left endpoint, any arbitrary left endpoint. So let's say -1 to infinity, and so on. And also we can extend it to the left-sided risks that go from negative infinity to an upper endpoint. Okay, so our framework are a bunch of losses that are supported from 0 to infinity, where S is their aggregate. And let's just define what we mean by VAR sub-additivity, super additivity, and additivity, just to have a concrete framework. So we say X, the random variable X, the random vector X, is a VAR sub-additive if the VAR of the sum is less or equal than the sum of the VARs for every probability threshold P between 0 and 1. And we say X is VAR super additive if the inequality is reversed. And when we say X is VAR additive if the equality holds for every P. Okay, so let us deal with the first part of our question. So let's go back to our question. Our question was, under which models we have VAR sub-additivity, additivity, super additivity across all confidence levels P. And let's start with the sub-additivity / additivity part. Before we do that, let's define one concept, and that is the comonotonic concept. We say X as a random vector is comonotonic if its joint CDF is the upper Frechet bound. I believe you are familiar with this dependence structure. So if the joint distribution of our random vector x can be expressed as the minimum of the marginal distributions, and this is the, if you will, the top, the extreme positive dependence that we can have. Okay, it is an extreme dependence, extreme positive dependence. And it is a well-known result that if x, the random vector x, has a joint CDF that is comonotonic, then the var x is var additive, because var of the sum is exactly the same as the sum of the vars. This is a well-known result in the literature. All right. So let us answer the first part of our question. It turns out that var subadditivity for our right-sided random variables that start from 0, it holds if and only if var is exactly additive. And that can occur only under x being comonotonic. So this is essentially an impossibility theorem. And it says var cannot be subadditive for all probability levels, for all confidence levels, P, because it is exactly the same as additivity. And that can only occur if our random vector is comonotonic. And this is quite a restrictive statement, right? It tells us that no matter how hard we try, we cannot find a model for which we have var subadditivity. I mean, at least one of the P's will give us strict subadditivity in the sense that var of s is strictly less than that. If we assume this holds for every P, then it must be that equality holds for all P. And additionally, x must be comonotonic. Okay, so for right-sided random variables, it's impossible to have subadditive models. So how can we interpret this result? It means that diversification across all P, we cannot have that for right-sided risks under var. Okay, so because subadditivity cannot happen. In this theorem, our theorem, we did not require any sorts of integrability for the random variables. Integrability of random variables means that they have a finite expectation, or the finite mean. The expected value of each xi is finite. That means we have integrable random variable. So in this theorem, we did not assume whether they are integrable or not non-integrable. Okay, now our result here is an extension of an earlier result from Imamoglu and Kato, where they had this elegant result in their paper, where they stated that if x is any random vector, not necessarily right-sided, left-sided, could be real, supported on the whole real line. And if we suppose that each xi is integrable, that is, its expectation is finite, then var subadditivity is equivalent. In fact, also superadditivity, var superadditivity is equivalent to additivity. So x must be comonotonic. Again, if we start with a random vector, no matter where it is, no matter what its support is, if each component is integrable, then subadditivity or superadditivity is equivalent to additivity, or x being and x being comonotonic. Okay, our result states the same. However, we don't require that each expectation must be finite. And it only works for right-sided random variables. So the proof for our theorem is very simple. First, we take the random vector x, and then we condition upon the sum being less or equal to to some k being a constant, a positive constant. That means each component is transformed to be xi given that s, the sum, is less or equal than k. And after we do that, then we prove that the new random vector, the truncated random vector, is the additivity of the original one is inherited to the truncated random vector. And after that, we know that once we truncate the random vector, then its expectation is finite, right? So it's integrable. And now we're back to the result by Imamuro and Kato. That means we have x being comonotonic and var is additive. Then we can take k, take the limit of k to go to infinity, and we recover the original vector and the original joint distribution, which must also be comonotonic. Okay, so this is it. So we have answered the first part of our question. var subadditivity cannot happen, and it's equivalent to additivity and x being comonotonic. And that characterization is for right-sided random variables. So I saw a question. How does var at the left side work if it is a quantile in the tail of a loss distribution that assumes mostly monotonicity? So you mean var is essentially the quantile, right? And you're asking about the left tail of how is var, for example, in here. If we have a standard normal, then var is simply the number for a given probability. Which number gives you that probability, right? The standard normal has negatives and positives. It's supported on the whole real line. So if you, let's say, if you are at -1, then the probability that we are below -1 is, you can use the empirical rule, right? So that would mean about 20 or 18. No, not 18. About that in that range. So about 16. So 16%. Okay. So if you say the var of 16%, you get -1. And as you move on from p from 0 to 1, you switch from negatives to positives. So whatever your distribution is, whether it's supported on the whole real line, whether it's supported on something that is from -infinity to some value, let's say 0, or from 0 to infinity, whatever your distribution is, your var will always be defined for p from 0 to 1. That is just the probability. It gives you the value for which that probability occurs, the CDF, the value of the CDF. So for example, if you have a random variable that goes from -infinity to 0, and you're asking about what is the var at p equals 50%, then that would be somewhere, it depends on the distribution, would be somewhere in the negative, let's say -5. And it will go up to 1 once you reach x equals 0, because that's your highest var. Yes, yes. So the loss distribution for the loss distribution is always positive. So it goes from 0 to infinity, right? Now your var at p equals 0 must be 0 because that's where you start. Your CDF at that value, your CDF at 0 is 0, right? It didn't accumulate anything. So the var at p equals 0 is 0. And then as you progress, as you move your p, let's say to half, to quarter, half, and so on, your var will increase. It will go from, let's say, from 0 to 2 and then to 4 and so on. And once, if your distribution is supported on the whole positive reals, so it goes to infinity, then as your p, the threshold p goes to 1, your var will go to infinity. Okay. So when p equals 1, that means the var is infinite in that particular case. But for us, we usually just say, if you remember here, our definitions, they exclude 0 and 1 just to be safe. But we could include them, that's fine. Infinity is just comparing infinity to infinity here. Okay. All right, so that's the first part of our question. Do you guys have any questions? Yes. All right, so now let's go on to our second part, which is the most interesting one. And the second is asking under which models is var super additive? Because now this is the area for which var has the advantage, right? Sub-additivity, not so much, because it cannot happen. But super additivity, it can. And this phenomenon of super additivity has been studied quite extensively, because under this assumption, var can amplify the risk under aggregation. So this is a flipped, if you will, like a flipped reasoning for diversification. So diversification actually increases risk in this scenario. So super additivity is, not intuitive in a sense, because it amplifies the risk of the aggregate versus the aggregate of the risks. And this phenomenon has been studied by a lot of authors, and quite recently, including Arab et al., Chen, and Schneer in 2026, and Mueller in his paper of super Cauchy distributions. But all of these literatures, they considered the case where each random variable is independent, mainly, not all of them, but mainly most of them considered independent, identically distributed random variables. So if you go back to our random vector, they considered X to have independent components, and each component follows the same distribution. So they have identical margins. And they mainly use the machinery of stochastic orders. So they obtain their results by asking this question, whether x being an independent copy of one of those variables, because they all follow the same distribution, right? So x is another independent copy. If x is less or equal than the convex sum of all of those. That's a good question. So someone asks, what happens to derivative hedging if you increase your risk? If super additivity means that diversification increases the risk. And you can see that super additivity will break most conventional models. Let's not go far to derivative hedging. Let's think of, like the mean variance optimal portfolio theory, right? Then once you go to that realm of super additivity, these concepts no longer work under these models. Okay. In derivative hedging, usually we consider, I think, exponential, or what do we call them? Sorry, log normal distributions. Usually, if you're following Black-Scholes model, then in that case, we don't have that super additive scenario here. And under all theories in whether economics or finance, if you go to the theories of, let's say, capital asset pricing model, it relies on the assumption that the expected value is finite. And sometimes the variance is finite, because we need that law of large numbers to work. But super additivity, as we will show in a moment, happens when we have infinite means. And that is a realm where all existing theories do not work in. So it is different than what we have. And that's why it is unintuitive or counterintuitive, in the sense that it amplifies the risk of diversification. So the message for risk managers is that if you have a model that exhibits super additivity, you cannot use any of, let's say, the hedging strategies or your pricing models that you're familiar with, because the assumptions break down in that case. The finite meaning, the finite mean and finite variance assumptions. Okay, so super additivity happens quite naturally if we consider two things: the dependence structure being negative, we'll define that in a moment, and the tails, or the margins, need to be heavy-tailed. As you can see, heavy-tail means no means, no variances. And it cannot occur when all the components have finite means. Why is that? Because if you go back to Imamuro and Kato, the result here, if X has finite finite mean components, then super additivity of X is equivalent to just additivity, combinatoricity. And if we want to get a strictly super additive random vector, then at least one of the margins should be infinite. It should have an infinite mean. Okay, so this is a characteristic of super additivity, that the means, at least one of the mean, if not all, need to be infinite. And that's why most theories in finance and economics break down. Okay, so let's take an example just to illustrate where super additivity of var can happen. If we take two counter-monotonic variables, we just take the first variable being x and the second one being the reciprocal of x. So both of them have the same variable x, so they're not independent. We just take the component number one being x and component number two being the reciprocal of it. Then the joint distribution of that random vector x, which is bivariate, is the Frechet lower bound. That is the max of the sum of the two CDFs, -1 and 0. This is called the Frechet lower bound, which is the most negative dependence there is. You can contrast it to the Frechet upper bound that we defined here. This is the most positive, the extreme positive dependence that can occur. And in here, sub-additivity, as we said, is equivalent to additivity. But in here, This is the most negative dependence structure we can have. And if we take the component X being Pareto margin, Pareto of type 2, that means its CDF is given as 1 minus theta over theta plus X, all to the power alpha. Alpha is positive, theta is positive. Then we can work out the distribution of the reciprocal because they have the same source of randomness. Here X, and here is 1 over X. And you can work it out to be this CDF here. If we set alpha to be 1, just for simplicity, and theta, let's take it to be 2. Then we can work out that the var of the sum, remember now the sum is just X plus 1 over X. var of the sum is equal to this quantity here. While the sum of the vars, var of X plus var of 1 over X, is this, 5p over 2 times 1 minus p. You can work that out. Just take the inverse of those CDFs to get the individual vars. And then once you figure out the distribution of the sum, which is quite easy, you can take the inverse, which is the var here. And if you compare these two, you will see that var of the sum is strictly bigger than the sum of the vars for all p between 0 and 1. Okay, so this is an example that super additivity occurs under var for all p. So we have considered a strong negative dependence, and we have considered two Pareto distributions as margins. And it is worthy to note that when alpha is 1 for those two Pareto distributions, the expected value of the Paretos are infinite. I'm sure in some of you in your studies, you encountered this, right? Where you proved that the Pareto distribution has infinite mean when alpha is less or equal to 1. It's a standard property. Okay. So this example just shows us that there exists such models. And this specific example is not covered by the existing literature, right? If we go back to our in here, we said that most literature, most results in the literature consider independent, identically distributed random variables. But in our case here, the two random variables are not independent, first, and second, they're not identically distributed. Even if you take alpha 1 and theta being 2, you can work out that this one here is just, so if you take theta 2, alpha 1, then this is x over 2 plus x, right? And in here, the CDF is 2x over 2x plus 1. So the two distributions are not the same. However, there is no existing theory that deals with this. Okay. Now, let us just see what happens if we separate these two conditions. The dependence condition, which is negative dependence, and the margin conditions, which is the heavy-tailed phenomenon. So if we take this random vector, x equals the first component being small, this margin x, and then the second one being the reciprocal of x plus 1 instead of just x as the previous one, we add that 1. Now this is still counter monotonic. It still follows the same, it follows this dependence structure. So it is negative, very negative. So the first condition the first condition holds. However, the first x is, let's say x is Pareto type 2, where we take alpha and theta to be 1, just for simplicity. Then x is super additive. The first component x is a Pareto, which has infinite mean. However, the second one here is no longer a Pareto. It will be a uniform random variable that is between 0 and 1. And as we know that the uniform has a finite mean, which is half. So the first component has infinite mean, second one has finite mean. So you can see that even though we have negative dependence, but in here one has infinite mean, the other doesn't. And because of that, X is not fully superadditive. It will be superadditive only when P is less or equal than half, and then subadditive when P is greater or equal than half. Just like the examples we took from before, like the bivariate normal and the independent Bernoullis. So you can see that even the most negative dependence cannot guarantee superadditivity. Even though we have one component that has infinite mean, the other being uniform, it missed the interaction where superadditivity was broken for P greater or equal than half. Now let's do the other way around. Let's do it the other way around, where we consider infinite mean margins, both of them, instead of one, while the dependence is no longer very negative. So we'll take a random vector x with the joint CDF being given as a copula. If you're familiar with the concept of copula, it's basically a function that is defined on the unit square 0, 1, 0, 1. And then you can recover joint distributions once you plug in, instead of the arguments u or v, you plug in the CDF that you want. So if you take the copula, which is a function, whatever it is, it follows certain properties. And instead of u, you plug in f of x, x1. And then instead of v, you plug in fx2, x2. You get back a joint distribution. Now, suppose that both margins are Pareto 2, where where the shapes and the scales are 1. So they both have infinite means, right? Both of them. However, the support of the copula, as you can see, is this. This is no longer a purely negative dependence. Yes, you can see that this piece is negatively dependent, and also that piece is negatively dependent. But the overall dependence is a mixture between negative and positive, because they don't follow the opposite diagonal line, which is a characteristic of the counter-monotonic copula here, counter-monotonic distribution. So if you will, we diluted the dependence from being purely negative to being somewhat negative and a little bit positive. Okay, because they have a positive trend that way. And because of that, it turns out that X is no longer purely superadditive, because even though we have two infinite mean margins, both being Pareto with alphas being 1, right? Both have infinite means. However, superadditivity doesn't hold for all P. In fact, X is subadditive when P is between 0.275 approximately and half. Okay, so from this example and the previous one, you notice that a dependent structure by itself is not sufficient in general, and the heavy margins by themselves are not sufficient in general. So we need a joint dependent this specific interaction will give us R is super additive for every value of P. Okay. And the first condition deals with the dependence structure. We say X is negative simplex dependent if the CDF of the sum is less or equal than the product of the CDFs, the marginal CDFs. So that is a concept of negative dependence. This definition is weaker than the negative lower orphan dependence, which is a form of negative dependence which states that this joint CDF must be less or equal than the product of the margins. So this definition is a negative dependence definition. Okay, it encompasses a lot of notions, and one of them being the counter monotonic that we talked about, but it also covers ones that are not really strongly negative. Okay, and the second condition, which deals with the margins. So as we said, we need dependence and margins. We need the joint dependence and margin conditions. So the first one, this condition deals with the dependence requirement. The second one, this one, deals with the margin requirements. And the margin requirements we call the simplex dominance condition. If we define the function phi that takes in x1 to xn, gives us a negative number, and we define it to be the sum of xi times the log of the CDFs. Then we say phi is simplex dominant if phi of all of those x's is greater or equal than phi of s in every input, where s is the sum of all of those x's. So if this function defined here satisfies this property, that the phi of x1 up to xn is greater or equal than phi of s all the way to n, then we call it simplex dominant. Let me just share with you how do we visualize this property? It tells us that a function on those x's should be bigger than the value of the function at the point s in every input, in every argument. Okay, so I will skip then sorry, I went a bit longer than I expected. So just keep in mind, we have two conditions, dependence and margin conditions. Now, the main superadditivity theorem, which states that if X is NSD, negative simplex dependent, if our random vector follows this property here, and the margins are continuous, so we're not considering jumps, we're not considering discrete distributions, and if phi here, defined here, is SD, or simplex dominant, then the random vector must be superadditive for all P. And this is the main contribution of our result, of our work. You can see that it extends the existing results, where instead of having identical independent IID variables, to the case where we have negative simplex dependent variables, and they need not be identically distributed. They can be whatever, they can be a mix of different distributions. The margins do not need to be the same. Okay. The proof is straightforward. It's not too complicated. So we can just skip maybe this. The idea is basically to say that we need to bound the product of fxi, of the sum of the bars, by p, because we need to bound the CDF of the sum s of that sum of the bars by p, because fs of the var of s, as we say, if you take the CDF at the var value, you get back p. Because var is essentially the inverse function of f. So if you take f and its inverse, you get back t. So if the var is super additive, then it must satisfy this inequality. And the SD condition gives us this one at the top, while the NSD condition links the inequalities to give us the desired result. Okay. So what can we do? What can we do with this theorem? There is a nice condition that we can check. So the SD condition for phi is quite complicated sometimes, right? You have to check that this the value of phi here should exceed the value of phi here. One of the easiest way to check that is to consider the individual components of the function phi. So if each one of those components, if each one of those term of those sum is non-increasing, then phi would be SD. So we have only to check if x times log of fx is non-increasing, so in other words, it's going down, then the function phi, which is the sum of all of those, is simplex dominant. So this is convenient, right? We can check margin by margin. And there are many examples that satisfy this property where we have x times log fx is non-increasing, such as the Pareto type 2 with shape alpha less or equal than 1, Frischet with shape less or equal than 1, Levy, beta prime, inverse gamma, and a lot of those. One thing in common between all of them is that they all have infinite mean, right? And it turns out that when phi is non-increasing, then the mean must be infinite. And you can check this argument here. It's quite straightforward. Okay, finally, what if we start with x that is already superadditive? Specifically, if it's negative lower orphan dependent, where each phi is non-increasing, so it's SD, and this one is NSD. That means it's superadditive. If we take transformations of our original random vector, which is strictly increasing, convex, and centers the zero, then the transformed random vector is also var superadditive. So var superadditivity is invariant under strictly increasing convex transformations of the margins. All right, I think we are out of time, but the last takeaways of this talk, we have shown that var subadditivity is essentially impossible for right-sided risks. Superadditivity is natural and characterizable. Specifically, we characterize the negative simplex dependence and this simplex dominance as two criteria for superadditivity, and both of them play a role in risk management. Finally, we showed that superadditivity is invariant under increasing transformation. And lastly, we didn't show this, but the results are reversed for left-sided variables. So those are supported from, let's say, negative infinity to 0. That means superadditivity will be impossible, where subadditivity will be possible in that case. Okay. Thank you all for listening. Any questions?
Yeah, thank you so much, Professor. Yeah, Justice, please go ahead with your question.
Yeah, so I would like to ask if the presentation slide can be shared so that we can sort of go through the proof thoroughly for those who are interested.
Sure.
Okay.
I can share it in the chat as well as the paper itself.
Okay.
Do we have any more questions?
You can ask whatever you want.
Okay, if there are no more questions, thank you so much for joining today. And thank you, Professor, for delivering such an insightful and engaging session. It was truly valuable, and I'm confident all of our participants took away a lot from your expertise. We really appreciate you taking the time to be with us and to share your work. Thank you for being a part of today's event, and we look forward to welcome you back for future talks.
Thank you.